Okay, good afternoon, everybody, and thank you for having me here. So today I want to give you kind of a brief introduction about the Earth's interior and how it affects what we see around us, okay? But before I do that, let me ask you, so are you familiar with Earth scientists? What is Earth sciences, do you think? Or how many Earth scientists have you met? So, okay, it doesn't matter, but I'll just anyway give you an introduction. So who is an Earth scientist? So an Earth scientist is someone who studies the sciences related to the Earth, okay? So we use diverse tools such as physics, chemistry, even mathematics, and biology to understand how this planet works, right? So this is, it's an applied science, and so whatever your background may be, okay, whether you're doing mathematics, whether you're doing physics, or anything else, you can actually apply your knowledge to the field of Earth sciences if you want to know something about this planet. So I'll start with this image of the Earth, which is taken from a Russian satellite. It's a very iconic image, and it's a very beautiful image. And you see that there are various things that stands out. So you have the oceans, so you have these oceans, the blue oceans, and you can see these white clouds swirling over them. And also if you look at the continents, you can see that there are differences, right? So different land masses appear differently. So let us look at the Indian landmass. So what you have here in the south looks very different from what you have north of it. And we know what's here in the north of India, it's the Himalayas and the Tibetan Plateau, right? The highest mountain ranges in the world. So, okay, so let's zoom into this region, and so this is again India, and you see the Himalayas rising above it to the north. And you can see the stark difference, right? So most of the Indian landmass is flat. Well, not actually flat. You do have topography, you do have mountains, but compared to the Himalayas and what lies to the north, most of this landmass is flat. And then as you go north, you see this wall of mighty mountains. So Earth scientists ask these kinds of questions like, why are the Himalayas here? What created them? Why do we have them here and not somewhere else? Okay? And so it's not just a difference in topography as you look at this region. If we also look at the earthquake distribution, we see that they are very different depending on where you are. So what I show you, these circles, these red circles, are each earthquake sources, each earthquake source, right? So each red circle is an earthquake that has occurred. And the size of the circle tells you how big the earthquake is. So you can see most of the India has very few earthquakes. And even if there are very small in magnitude. But again, if you go to the north, you can see that there is a very dense cluster of earthquakes, okay? So again, it's not just that you have mountains and flat land. You also see that things like earthquakes, which everybody, and which affect us, common people, and they are also different depending on where you look. And so it's not just this particular region. If you also look at the global earthquake map, and this is an earthquake distribution on the Earth between 2000 to 2009, and which shows you only earthquakes of a certain magnitude, greater than the certain magnitude. And here again, you see that these earthquakes are only restricted to certain regions. They are not uniformly or evenly distributed all over the world. So most of them are in the oceans, And even in the continents you have, and even within these oceans, they are occurring in very narrow bands. And within the continents, the distribution is a little more diffuse, but you can see there are large swaths of land which has almost no earthquake, but then there are regions like here, the Himalaya, the Tibetan Plateau, and then Africa, Western North America, and all these regions have a lot more earthquakes. So again, why is that? Why do some areas have so many earthquakes? Why do some areas don't have earthquakes at all? So again, question very relevant to an earth scientist. Let's look at some other observations. So here I show you the ages of the rocks that make up the ocean floor. So we can actually, people have mapped the ocean floor pretty accurately. And as they have mapped, they have also dated the rocks that are lying on the ocean floor. So they have used radiometric dating, a particular kind of radiometric dating called potassium argon, because you find a lot of potassium in the rocks on the ocean floor, which disintegrates into argon. And based on that radiometric dating, you can actually date the ocean floor and figure out how old it is. And this color bar at the bottom shows you the age of the ocean floor in million years. So you can see it starts from 0 and it goes to 280 million years. So you see these red regions are very, very young ocean floor. Okay, and as you move away from these regions, the ocean floor gets older and older. And also something to remember is that the average age of the ocean floor doesn't go beyond 200 million years. So the age of the Earth is about 4.5 billion, but if you go to the oceans, you don't find rocks which are older than 200 million years. Okay? Why? We will come to the answers to these questions later in the talk. And where you find these really young ocean floor, these are called the mid-oceanic ridges. So these are ridges that run right through the middle of the oceans, and that's where you find very, very young rocks. Okay. So, so as I said, that you don't find rocks older than 200 million years, and okay, so before the continents, okay, so if you also look at the heat flow distribution within the oceans, you can see that the regions which are very young have higher values of heat flow. So again, these are the red regions, which is very high heat flow. This is in milliwatts per square meter. And as you go away from these mid-oceanic ridges, the heat flow values decrease. Okay. But if you go to the continents, on the other hand, you can see that the heat flow distribution is much lower. So what about the ages of the rocks that make up the continents? So here is, I'm not showing the ages for all the continents, but these are some specific areas of the continents which are marked here in dark and light green. And these areas are called the cratons. And there you find the oldest rocks on the surface of the Earth. These rocks are as old as about 4 billion years. Okay, so in the oceans, you don't find rocks more than 200 million years, but as you go in the continents, you get rocks which are almost as old as the age of the Earth. How does that happen? Okay, so this is these are the Archean and Proterozoic. These are two different geological eras. The Archean is the oldest era, okay, and that goes from 2.5 to 4 billion, and a slightly more recent is Proterozoic, that goes from 2.5 to 590 million to 2.5 billion years, right? So these are the areas where you find the oldest rocks on the surface of the Earth. And so this picture shows you how the surface of the Earth moves, okay? So these red arrows here are showing you the velocities of the Earth's surface. Now you can see that the velocity is not in same direction. They're all over. Different areas of the Earth are moving in different directions and also with different velocities. So here is the scale. This is 5 centimeters per year. So for example, you can see the Pacific is moving very, very fast at a rate of about 7 centimeters per year. On the other hand, if you look at, say, South America, it's moving at a much slower rate, okay? And on top of velocities, I also show you the regions of the measurement of strain rate on the surface of the Earth, okay? So these white areas are the regions where which has no deformation, right, which is not straining. And this colored region and the color bar tells you the values are regions which have a lot of deformation. So these are the regions where a lot of strain is going on, okay? And so what stands out from this picture that there are certain areas of the world where nothing much is happening, and there are certain areas of the world where a lot of activity is happening. And these are these colored regions where you have a lot of deformation going on. And if you remember a little about the earthquake map that I showed you earlier, the dense cluster of the earthquakes occur along these regions which have very high strain rates or which are undergoing very high deformation, right? Okay, so these are some of the observations that we can measure or we can see on the surface of the Earth. And again, Earth scientists ask the question, why? Okay, why is this a certain way? Okay, why not the other way? And the explanation to most of these lies actually not on the surface but deep inside the Earth. So we want to look what's going on inside the Earth, the processes inside the Earth, and those are the processes that control what's going on the surface. So let's take a look at what the Earth's interior looks like. Now this is again probably familiar to most people, right? This is a very simple cross-section of the Earth. So you have the crust, the topmost brittle layer of the Earth. Below that, you have the mantle, which is divided into the upper and the lower mantle. And then beneath that, you have the core, okay, and which is again divided into an outer and an inner core. And these distinctions are mainly based on composition. So all these three parts of the Earth are made of very different kinds of rocks. So for example, the upper part, the crust, is made up of mainly silicate rocks, which are very light, okay? As you go into the mantle, it is mainly made up of iron magnesium rich rocks, which are much denser. And as you go down into the core, it is mainly pure iron with a little bit of other lighter elements. So all these layering is based on the kind of rocks that make them. Now, the question arises, how do we know the interior of the Earth looks like this? The deepest borehole that we have ever dug was 12 kilometers in depth, okay? And the Earth's radius is 6,370. So, for example, the mantle starts at about an average 100-kilometer depth and goes down till 2,900 kilometers. And the deepest hole, as I said, that we have ever dug is only 12 kilometers. Somewhere in Russia, they wanted to dig more, but the temperature was so high. As you know, as you go down inside the Earth, the temperature increases. So the temperature became so high, there was so much heat flow, the instruments all malfunctioned, so they couldn't dig deeper. So that's the deepest that we have ever gone. So how do we really know that we have this core at starting at 2,900 kilometer, or you have the mantle starting at 100 kilometer, right? So we don't have any direct observation. So what comes to our rescue is earthquakes. I know earthquakes cause a lot of destruction. They're not liked by people, but the earthquakes are a great educational tool for those of us who want to study the interior of the Earth. So how does that work? So here is a kind of a schematic about how all this works. So suppose you have an earthquake at some point in Earth, and as once the earthquake occurs, it radiates out these waves. Okay, we call them seismic waves. So these waves travel through the Earth, and as they travel through the Earth, they get reflected and refracted at various boundaries. We call them discontinuities. And as they travel through the Earth, they carry information about the Earth's interior. And these waves, they get recorded at these stations. We call them seismic stations, and these recorders are known as seismometers. So once these, and we have seismometers all over the world. So once these waves get recorded in these seismometers, we can study these waves, and we can figure out what's going on inside the Earth. And this is what a reading of a typical seismometer will look like. So, so here what I'm showing you is on the x-axis we have time, and the y-axis we have different amplitude. Okay, so this is what a typical seismometer would record. So basically what it is recording is the ground shaking. So whenever you have an earthquake, the waves emanate, and as it reaches the surface, it's shaking the ground. And those ground shaking is being recorded by these seismometers. And by studying these wiggles, the amplitude of these wiggles, and also at what time they arrive on the seismometer, because you record the time at which these waves arrive at the seismometer. So based on those, you can actually map the Earth's interior. And you can figure out where are the discontinuities and what are the processes that's taking place. Now here is more a 3D view of what happens when an earthquake strikes. So this is an earthquake, this red dot that is originated at this point, and this is 25 seconds after the earthquake has initiated. And these are the different time steps. These numbers are telling you the time in seconds since the earthquake has originated. So this is 99, 213, and so on. So you can see how this is the wave front is propagating once the earthquake is initiated. So you see that these wave fronts, these waves are getting reflected and refracted and undergoing these kinds of patterns. And while they are getting recorded as seismometers placed on the surface of the Earth, they are recording these wiggles, right? And depending on the amplitude of these ground shaking and the time, as I said, we can figure out the Earth's interior. So the next slide shows kind of a way our understanding of the Earth's interior has evolved through time. So in 1906, this is all we knew about the Earth's interior. So we had the Earth, and then we had the core. That's all we knew in the beginning of the 1900s. And by the way, again, probably a useful piece of information, the core was first discovered by a female seismologist called Inge Lehmann in the 1900s. So she was one of the very, very first female geophysicists who studied the Earth, and she discovered the existence of this core. So anyway, so this is what our knowledge of the Earth's interior was in the early 1900s. And then by the 1970s, we knew that the Earth has many more layers. You have the crust, you have the mantle, then you have the core. And by 1990s, we saw that the crust, mantle, core picture that I showed you earlier is not that simple. You also have other discontinuities. And here I have pointed out some like 400 kilometer, the 670 kilometer discontinuity, and then you also have something called the D double prime, okay? So these are various other boundaries within the Earth, okay? And come to this century, we have seen that the Earth does not only have a layered structure, it also varies laterally. So it's not just a layered like a cake, but even horizontally and laterally, it has variation. So for example, this shows you slabs and the plumes. So slabs are basically very dense parts of the Earth, okay? And as they are dense, they tend to sink inside the Earth. And these plumes are regions of very hot, buoyant material. And as they are hot, they have low density and they tend to rise up, and sometimes in the form of volcanoes. So it's not only we have a very layered structure, but we also have very lateral variations. Okay? So this is what the present knowledge of our Earth is. Okay. So, so how does the velocity of these waves look like as they travel through the Earth? So as I said that we can image the interior of the Earth by looking at these waves that are recorded at a seismometer. So you're recording these waves, so you're recording the amplitude, you're recording the time of arrival, and we are also pretty good at locating the source of these waves, which are in other words the source of the earthquakes, okay? So we know from the source from which the waves have originated, and we also know the time at which it has arrived at the seismic station, and based on that we can figure out the velocity of these seismic waves. And this velocity of the seismic waves actually gives you also the velocity structure of the Earth. And this is what the typical 1D velocity structure of the Earth looks like. So for example, these boundaries I was talking about, the mantle, the core, the 410, 670, all this is reflected in this velocity structure. So what I'm showing you is the depth on the y-axis from the surface to the Earth's interior, and then on the x-axis we have velocity, kilometers per second. And these are the two different kinds of seismic waves. One is the P or the primary wave, and the other is the S or the secondary wave. So you can see there is a big velocity jump at this depth, very close to 3,000 kilometers. So this is where the mantle transitions into the core, okay? And again, close to 5,000, a little below 5,000, you again have a jump. And this is where the outer core transitions to inner core. And also if you look at the shallower depths, you see these small jump in velocities. And these are because of these discontinuities that I was talking about. You have the discontinuity at 400 kilometer, discontinuity at 670 kilometer. So as soon as these waves encounter a discontinuity or a boundary, there is a change in velocity. And from this change in velocity, we can figure out that this is how the Earth is layered. Okay, so I showed you a few observations, and I talked a little about how the Earth's interior looks like. So then, how does this help us in explaining what we see around us? So let's get back to our original question about the Himalayas. So why did the Himalayas are there in the first place, and how did they get created? So I'll show you an animation okay, so this animation starts at 60 million years before the present, okay? And what I'm showing you here is a vertical profile of the Earth taken along a north-south direction. So you have India in the south and Asia to the north. And what's you can notice here that India is not a part of Asia, okay? So at 60 million years ago, India was not a part of Asia. And instead, these two land masses were separated by an ocean, okay? And let me start the animation. So see what happens with time. So India is moving towards the north, it's colliding with Asia, and there's a lot of deformation, shortening, compression going on, and this is where the Himalayas are now, okay? So the Himalayas are created because of this northward collision of India with Asia. So how did we know that? What would tell us what happened 60 million years ago? So some of the clues are in the Himalayas themselves. So if you go and look at, if you ever go into the Himalayas and look at the sediments there, you can find a lot of marine fossils, okay? So you have fossils of organisms which used to live in the oceans. So how do you find organisms which live in the oceans on the top of the highest mountain in the world? It doesn't make sense. The only way it makes sense is that these were not here for eternity. These Himalayas were actually formed from the sediments that were found at the bottom of the ocean. That ocean that I showed you that existed between India and Asia, that ocean closed up, and the sediments that were at the bottom of the oceans, that all got uplifted, and that formed the Himalayas and the Tibetan Plateau. And that's how we find marine organisms in the Himalayas, fossils of marine organisms in the Himalayas. Now, also as start this animation once more. Now, also see that this oceanic part, okay, and you can see this dark structure that is dipping inside the earth, okay. There is actually the part of this oceanic lithosphere which is diving inside the Earth's mantle. So why is it diving inside the Earth's mantle? Because it's very dense, it's very heavy. So if an oceanic lithosphere and the continental lithosphere collide, the oceanic lithosphere is made up of much denser rocks. So what happens? The denser lithosphere sinks inside the Earth, okay? And that's what it's shown by this dipping structure. So this oceanic lithosphere once existed, and it sank inside the mantle and just disappeared. So now we don't have any trace of the ocean on the surface except for these sediments. Okay? So again, how did we reconstruct this movie? Okay, so yes, the sediments with the marine fossils helped us, but how do we know, for example, the oceanic lithosphere dips like this? So now if we come and look at the present day Earth, so here is, I show you again a vertical profile, and that is taken here somewhere in the Pacific, close to Indonesia, okay? And what I show you here is, again, the vertical axis is depth, so it goes from the surface to 700 kilometers, and the horizontal axis is the distance. And these yellow dots that you see are individual earthquakes, okay? So what I'm showing you is the earthquake distribution that is occurring with depth at this region of the Earth. So what do these earthquakes tell you? So we can see that they very nicely mark out a dipping structure, okay? So this is true not only in case of this particular area. If you look at many places on the Earth where you have an oceanic lithosphere that is colliding with a continental lithosphere, you see these kinds of dipping structure. So we kind of, from there, we can kind of figure out a three-dimensional, in 3D, what could be happening, where you have two, the oceanic and the continental lithosphere colliding, and the denser lithosphere, which is the oceanic lithosphere, dipping inside sinking inside the Earth in this dipping fashion. Now, this particular slide shows you the, so based on these, we can come up with this model of a collisional boundary. So this is basically shows what I just told you. So you have the oceanic crust, and then you have the continental crust. As they collide, the oceanic crust dips down, being denser, and often because of this collision, it creates these mountain chains at the boundary. And these, as I said, these are called the collisional boundary, or sometimes also known as subduction zones. And these are pretty common throughout the Earth. So for this figure shows you the subduction zones on the Earth. So these black lines with the teeth on them, these are the walled subduction zones. So you can, for example, you see here in the Himalayas, and then you also see all over the Pacific, and then western part of North America, then western part of South America, where you have the Andes. These are all subduction zones, or collisional boundary, where you have this process going on, where two plates, they are colliding, and this denser oceanic plate sinking down inside the Earth. So we looked at the earthquake distribution that kind of told us about how this oceanic lithosphere would look like at depth. Now, these earthquakes also gives us, there's another way of telling what's going on in the subduction zones, now by looking at the velocity of the waves that these earthquakes emanate. So in the last slide, I just showed you the earthquake locations that kind of defined the existence of this dipping lithosphere. And here I'm showing you the velocities that we can image based on these earthquakes. So what this picture shows you, again, this is a vertical profile, a cross section, and goes from the surface till 700 kilometers, and here is the distance. And here now we are looking again somewhere in the Pacific close to New Zealand. This is a place known as the Lau Basin, okay? Here the Pacific plate is subducting along the Indo-Australian plate. And these colors tell you the velocity anomalies with respect to some kind of a reference. So what this means is that how fast or slow these regions are with respect to some reference velocity. So this blue color tells you that this is a very fast region, which means that the seismic waves traveling through this region will travel much faster than the surrounding regions. While the red color shows you slow regions, which means the seismic waves traveling through these regions would slow down. And also we know that the velocity also, the velocity can give us an indication of the density structure, which means that if your velocity is high, your density would also be high. So now this all adds up. So this is a high velocity structure, means that this also has very high density compared to the surroundings. And this is, so this is basically then this is the oceanic lithosphere, which is dense and which is sinking. So you can see that from various different kind of observations, we kind of try to, we try to build a three-dimensional picture of the Earth's interior. Okay, so, so far I talked about earthquakes. Now, is there anything else besides earthquakes that can tell us about these kinds of movements or phenomena? So another important observation comes from GPS. So you're all familiar with GPS, you have GPS on your phones, but this is what we call this permanent GPS network, right? So this is what a GPS station looks like. So you have the GPS antenna, and then you have the solar panel. This is a GPS station in the Sierra Nevadas in North America. So the GPS basically measures the movement of the of any particular place, right? With based on your satellites. And if you have two plates which are moving towards each other, and you have GPS stations on both the plates, with time you would see that these two stations are moving with respect to each other, moving closer towards one another. So GPS also helps us in trying to understand these movement of the Earth's surface. And here is a picture of the global GPS distribution on the surface of the Earth. So these are the permanent GPS, not permanent I should say, this gives you a time series. So some GPS has been active for 22 years, some for much fewer years. But these are the GPS stations located, and it's an uneven distribution, but still it kind of gives a pretty good idea about the movement of the Earth's surface. So so far I talked about this collisional boundary or the subduction zones, where you have the oceanic plates that get destroyed as it sinks inside the Earth's interior. Now let us look at another part of the Earth, and this is Iceland, a beautiful place that sits very north in the Atlantic Ocean, north of the Atlantic Ocean. And here I show you two GPS stations on two different parts of Iceland. Okay, so the one in Reykjavik and the other is in Hofen. Now, what's interesting is if you look at the data from these GPS stations, these two GPS stations, we see that this station is moving towards the west, while this station is moving towards the east. Now, both the stations are on the same landmass on Iceland, but one is moving one way, the other is moving the other way. So what does that imply? The Iceland is splitting apart. Is that reasonable? It is reasonable. Why? Because Iceland is, apart from being a very beautiful place, Iceland is also very unique in that it sits right on top of the mid-oceanic ridge. So remember I showed you the mid-oceanic ridges where you have plates that are, you have very young rocks. And this mid-Atlantic ridge actually passes right through the middle of Iceland. Okay? And as you know, the Iceland is pretty famous for its volcanoes. You have a lot of volcanoes in Iceland. And the reason for this is because of this mid-Atlantic ridge that passes through Iceland. So this is probably a better way to look at it. So here is the bathymetry, and here you have the mid-Atlantic ridge, and this is where Iceland sits. Okay, so you can see that the ridge passes right through the middle of the continent. So it's actually an oceanic ridge, but it has come up, right? Okay, because so the Iceland was probably once beneath the water level, and it has come up, and that is why you have the oceanic ridge that is exposed on the surface of the Earth. So, so as I said that you have two stations that are moving on different sides, which means that the country is splitting apart. And that gives us the model of a divergent plate boundary. So what happens in a divergent plate boundary? So you have two plates, and which is separated by this kind of a ridge. Mostly it is found in the oceans, but you can also find it in the continents. So you have magma rising, and you have these two plates that are splitting apart or moving away from each other. Okay, these are known as the divergent boundaries. So these are the places where you have the youngest rocks, these are the places you have a lot of volcanic eruption, and these are the places where you have new crust that is generated on the surface of the Earth. So subduction zones, so collisional boundaries are where crust gets, or the Earth's surface gets destroyed, and these divergent boundaries are where the Earth's surface get created. So we have creation and we also have destruction, okay? And so I showed you this figure earlier. So these are where the mid-oceanic, these divergent boundaries lies. So again, all this makes sense because oceanic crust is getting created. You have very young ages of rocks in these regions, right? And with time, as they spread apart, these rocks become older and older. Okay, so we talked about boundaries getting, talked about collisional boundary, we talked about divergent boundary. We also have a third kind of boundary known as the transform boundary. And these are the regions where the crust neither gets created nor gets destroyed, but you have two plates which move past each other, okay? So you can see this plate moving this way and the other plate moving that way. So it's kind of a lateral horizontal motion, okay? And a very famous transform boundary on Earth, maybe some of you have heard about it. This is the San Andreas Fault, which lies at the boundary between North America and the Pacific Plate, okay? So here is San Andreas, and again it is famous because of earthquakes. It's a very, very highly earthquake-prone zone in this world, right? So we have very populated cities, and they're expecting to have a big earthquake which can occur anytime, right? And this is again because of these two plates that are sliding past one another. And so I also thought I would show you what the San Andreas Fault looks like. Now, this is a feature that spreads for thousands of kilometers, and it cuts through the Earth, and it's very, very prominent. So if you're flying over this part of the world, this is what the San Andreas Fault would look like. So if you're flying in a plane, going from west to east, or the other way around. So you can actually see the trace of the San Andreas Fault on the surface of the Earth, okay? And this is, this region marks the boundary between the North American and the Pacific Plate, okay? Okay, so why do we care about these three different kinds of plate boundaries? If you're not just for curiosity's sake, we care because these different kinds of boundaries means different kinds of earthquakes. So if you, again, this is an earthquake distribution map that I showed you earlier. And where you have these collisional boundaries, where two plates are colliding with one another, the subduction zone, these are the regions where you have the largest earthquakes, okay? So if you're living very close to one such boundary, so for example, if you're very close to the Himalayas in North India, for a person say living in Delhi, you have to worry about what kind of plate boundary you're next to, because that would mean what kind of risk from an earthquake do you have. On the other hand, if someone lived next to a mid-oceanic ridge, it really doesn't matter because the earthquakes that occur along these divergent plate boundaries are much smaller, okay? These are much smaller in magnitude, so it's not really going to cause much damage. And then somewhere in the middle lies the earthquakes along these transform fault boundaries, so somewhere like along the San Andreas Fault. They also can give rise to very big earthquakes, but not as big as in the subduction zones, okay? So for example, the biggest earthquake that has been recorded so far was in 1960 in Chile, where you have this South American plate that is colliding against this plate, which is known as the Nazca plate, okay? So that was, I think, a 9.6 magnitude earthquake, and that's the biggest earthquake we have recorded so far, again at a subduction zone. And some of you may have heard about this 2004 tsunami that, and that also originated because of an earthquake in Indonesia, in Sumatra, right? And that was also a very big 9.6 magnitude earthquake. Why? Again, these are all subduction zones, okay, where one plate is dipping, sinking inside the Earth's mantle. So if you're close to the subduction zones, you worry about being affected by a very big earthquakes, right? If you're situated close to a divergent plate margin, you probably don't care so much. Okay, so just a explanatory slide about how the earthquake occurs. So this is known as based on something called the elastic rebound theory. So basically, if you have two plates and one is moving in one direction, the other is moving in the other direction, it will build up a lot of strain energy, right? And the strain energy will continue to build up, and at some point, all this energy will get released in the form of an earthquake, right? And that will give rise to ground shaking, and this release of energy will causes a lot of destruction from the earthquake. And once the entire energy is released, the rocks rebound to their original shape. Okay, so that's how earthquakes basically occur. So here again, I put up this slide of the plate velocities and the strain rates. So there's different kinds of plate boundaries that I talked about. So these are, all this came together to give rise to this concept known as plate tectonics, which again, probably you have heard about, okay? So the plate tectonics tells you that the Earth's uppermost layer is broken down into different blocks or plates, which move in different directions with respect to each other. And the interior of these plates are undeformed, not much is going on, but these plate boundaries are where you have a lot of deformation. And it is these plate boundaries that I've been talking about for so long, these different kinds of plate boundaries, the collisional, the divergent, and the transform boundaries. And it is these boundaries where you have, where you find most of the earthquakes, okay? And all these surface motions have their origin in what's going on inside the Earth. And here is a cartoon showing a typical subduction zone. So here you have an oceanic lithosphere that dives inside the mantle, and this also shows you a hot mantle plume that is rising from the depth, and that is splitting apart an ocean. So there's all these surface movements, the topography, the plate velocities, the earthquake occurrence, their magnitude, everything is controlled by actually what's happening inside the Earth. So you have churning going on inside the Earth, you have convection going on inside the Earth because of these difference in densities. You have these dense masses that are sinking, and you have lighter masses that are rising upward. I mean, because of these density differences, you have this convection processes going inside the Earth, and that's what controls what we see on the Earth's surface. Okay. So how much time do I have? Like 5 minutes? Okay, yeah, so that's enough. Okay, so I'll show a couple of slides about how the Earth's interior looks like with depth. So what I'm showing you, so far I've been showing you cross sections, vertical profiles, and here I show you the map view. So the lateral variation of velocities inside the Earth at different depths. So these are basically 3 different models. So we won't get into it, but you see these how the velocities are varying at 3 different depths: at 140, at 925, and at 2,700 kilometers. And these colors again show you how fast or slow the region is. So if you look at the 140 kilometer depth, you can see these really slow velocities, and these are because of the mid-oceanic ridges, where you have hot material which are rising up, so they are less dense, hot, and giving rise to these divergent plate boundaries, right? But also you see that as you go down inside the Earth, the picture is very, very different from what you see in the shallow part of the Earth, right? And we still don't understand why the Earth looks like this at this depth. So we still don't, I mean, of course, we have some theories, but we still don't have a clear understanding as we go deeper inside the Earth, what controls these kinds of phenomena. For example, you see these very low velocity regions. So these are the very slow regions in these huge regions at very close to the bottom of the mantle. And we don't know why we have those regions, what creates them, and why are they sitting here. So there are many things we still don't know about the Earth's interior, and whether they might have some control on what we see from the what we see on the Earth's surface. Okay, so I'll just leave with some questions that we still trying to address in earth sciences, especially in the field of earth sciences that deal with the Earth's internal processes. So I showed you how the material properties inside the Earth, like the density, controls the convection inside the Earth, and that in turn controls the movements and the observations on the surface of the Earth. There is another important material property called viscosity that also controls how this convection would occur. So viscosity is basically tells you how strong a particular region is. So something that has a very high viscosity would mean that it won't flow easily, and something has a low viscosity, which means that it will flow easily. And this density and viscosity are two of the very important properties that control the Earth's internal processes. We have some idea about the density structure based on these seismic velocities that I had showed you, but when it comes to viscosity, we are at a loss, okay? We just don't know what kind of viscosity structure inside. Again, we make, somebody like me make numerical models in order to understand the viscosity structure, but again, these are models. We don't really have any verification that this is what the Earth's viscosity structure look like. So I talked about these large forces that makes plate moves, plates get destroyed, plates get created. So what are the forces that drive these plates? Now, of course, convection in the mantle is an important aspect, but the plates themselves also can play a role, okay? And we still don't have a clear understanding about how these forces kind of, we don't have a clear understanding of the quantification of these forces. So how big are these forces? How big are the convective forces in the mantle versus the forces that's driven by the plates? A very important question and a very popular question nowadays is how plate tectonics initiated on early Earth. And why is that important? Now it is believed that because of plate tectonics, we have life on Earth. So all the kind of, the missions that we send out, they now look at evidence of plate tectonics in the outer planets, because we believe that because there was plate tectonics, we have life. So without plate tectonics, like we don't have plate tectonics in Mars, we don't have plate tectonics in Venus, and we haven't seen any signs of life there. So, but how did plate tectonics initiate on Earth? We still don't know. We know that we have a present-day plate tectonics, but we don't know how it all started, okay? And so all these kind of relate to this final question of this, how the deep Earth interacts with the surface. So, okay, I guess I'll stop here and hope I've given you kind of an outline of Earth, what Earth scientists do, and feel free to ask me any questions if you have. Thank you.